So we're going to continue with the evidences for the formation of benzyne intermediate as well as the reaction mechanism path, that is elimination addition during nucleophilic aromatic substitution reactions. Okay, so if you could remember, we had seen a fact that when deuterated fluorobenzene is converted to aniline very slowly, but it loses its deuterium rapidly to give back your fluorobenzene. Okay, so now we are going to see if this is the case when bromine is the atom attached to your benzene. That is, this case is prominent with fluorobenzene. But what happens if I have bromobenzene and when that is subjected to the very same nucleophilic substitution reaction? Okay, so it was found that in case of orthodeuterobromobenzene, the breaking of this particular bond, the carbon and bromine bond, was faster. That is because the carbon-bromine bond is weaker when compared to your carbon-fluorine bond. This is a strong bond, okay? And hence, this reaction, if you consider the rates of leaving of this fluorine, that is pretty slower. But in this case, CBr bond breaks quickly and this is the fast step. Okay, so the formation of your carbanion intermediate becomes a fast step, and as soon as it is formed, this being bromine in this case would get eliminated quickly. So there can be an instance that the step 1, that is abstraction of proton, followed by the elimination of your bromide ion, takes place simultaneously, or you can say that the step 1 and step 2 might be concerted, and that is because of the weak strength of your carbon and your bromide bond. Okay, but this is different when you consider the X, the halogen, to be fluoride. This is a faster step, and hence these two steps does occur in case of fluorobenzene, but in case of bromobenzene, these two steps becomes concerted. Okay, that means it occurs simultaneously. Now, we had seen another fact that metabromoanisole, whereas orthobromoanisole led to the very same product, that is meta-anisidine, and we left with what would be the intermediate that is involved during the course of this reaction. Okay, we had interpreted that this as well as this would proceed via the very same mechanism, the very same intermediate, to give you your same product, that is meta-anisidine. And we had wondered that what kind of benzyne would have been formed during the course of the reaction. Now let's see what is the benzyne that is formed when metabromoanisole or your orthobromoanisole is subjected to nucleophilic aromatic substitution with amide as the nucleophile. Okay, so which benzyne is it and how meta-anisidine is formed? To deal with this, we need to check the orientation of both of these benzynes in the elimination stage, and the addition stage. We must remember that a methoxy group over here, a methoxy group, this is electron withdrawing by resonance, okay, whereas it is electron donating by resonance, whereas electron withdrawing by inductive effect. You even know that inductive effect operates in the space through sigma bonds, okay, and the resonance effect operates via the pi bonds. Okay, now in this case, the new benzyne that is formed, that has a new bond which lies towards the sides of this benzene ring. Okay, it does not have direct interaction with this cloud of electrons, the pi cloud of electrons present either above or below the ring. Okay, so this is not going to get into conjugation with the electrons that is involved for resonance. Okay, so in other words, I can say that OCH3 group does not involve in resonance. The electrons on oxygen does not involve in resonance, and the only effect that operates is via your sigma bond, and that is the inductive effect. Okay, so in case of your bromo substituted molecule, you should be sure that there is only one possibility, that is, after the abstraction of proton, your carbanion should form only in this particular position. Okay, because in previous facts we had seen that it is the ortho position or the ortho proton that gets involved during the benzyne formation. So we have this position as well as this position. This position is already blocked by your O-methoxy group, whereas this position, it has a proton which can be abstracted and a carbanion is formed over here. Okay, the next case would be when bromide is eliminated, this has to get delocalized over this carbon-carbon bond, and this would further eliminate bromide ion. Okay, but what happens in the case of your metabromo anisole? Over here we have two possibilities for proton abstraction. This ortho and this ortho proton, they are susceptible to abstraction in presence of a base. Okay, so either the carbanion can be formed either in this position or it can be formed in this position. But we have a methoxy group which is electron withdrawing, which has an electron withdrawing effect. Okay, so this is closer to this particular proton rather than this proton. As a result, if a carbanion is formed in this position, then this O-methoxy group will attract the electron towards itself, further stabilizing this particular carbanion more than it would do with this particular carbanion. As a result, the more stable carbanion by the abstraction of a proton in between your bromine and your methoxy group takes place. So this benzyne is more likely to be formed during your course of the reaction. So in your metabromoanisole case, this is the benzyne, and in case of your orthobromoanisole, this has only one possibility of forming a benzyne, and this is this one. So your structure 3 as well as this structure is one and the same, and since same benzyne is formed, either you take your orthobromoanisole or your metabromoanisole, the product is also one and the same, that is meta-anisidine. Okay. So for references, you can see to your organic chemistry book by Robert Thornton Morrison and Robert Nielsen Boyd. Okay, I have taken all the parts of this particular topic from the very same book. Okay, so that's one of the best books which you can refer for your graduation. Okay, thank you.